This is FRQ number 1 on the review packet for oscillations and waves. It reads a simple pendulum consists of bob of mass 0.085 kilograms attached to a string of 1.5 meter. The pendulum is raised to point Q and then released so it oscillates with a small amplitude between points Q and P as shown below. On the figures below, this is part A, draw the free body diagram showing and labeling the forces. So I have to draw them in and I have to label them. And they want me to do it when it's at point P for little part 1. So I know that there's going to be a force up and to the left, and then I need to label that force. I'm going to call it the force of tension, Ft. There's also a gravitational force acting down. I can just call that one mg, or alternatively I could call it F sub g. When it's at the lowest position, there is still a gravitational force, mg, and the tension force is straight up. It's got to be larger, and so that would be my free body diagram at the lower position. They want me to calculate the speed v of the bob at the lower position. That's a conservation of energy question. We know that there's going to be gravitational potential energy at point P, and I'm going to compare that to this equilibrium position right here, and we know that all of the energy there is kinetic energy. This becomes mgh is equal to 1/2 mv squared. Once I make the substitutions, I can see that the mass doesn't affect the results, and I can multiply both sides by 2. This becomes 2gh is equal to v squared, and then I'll just take the square root of both sides. That should look familiar to you. You've seen that before a few times. When I substitute some numbers in, this becomes 2. I'll leave the units off to make it easier to see. 9.8 times the height, which is 0.08 meters. And when I multiply those things by each other and then take the square root, I get 1.25 meters per second. So that is the answer for the speed, how fast it's going in part B at the lower position. It then goes on to ask, what is the tension in the string at the lower position? This is bringing us back to circular motion. I'm going to ask you to take a look at the free body diagram that we took. When objects are moving in circular motion, there's always a leftover or center-seeking force. We know that this is an arc here, so it's in circular motion at the bottom. There needs to be a leftover force, which we call a centripetal force, directed radially inward, or in this case, in the upwards direction. I'm going to call upwards positive, or the center of the circle positive. In my dynamics equation becomes Ft minus mg is equal to my leftover force, or the centripetal force. So I know that the centripetal force can be written as mv squared over r. So I'm going to go ahead and do that. I'm solving this for Ft. I'm going to add mg to both sides and substitute. This becomes Ft is equal to the centripetal force, which is mv squared over r plus mg. Now, interestingly, I just solved for an expression right here, root 2gh, when it's at the lower position. So I know how fast it's going to be going at the lower position. I could, if I wanted to, factor out the mass variable if I wanted to. So let's go ahead and do that. It's going to be m times v squared, which is just root 2gh. And I have to remember to square that. So it's root 2gh squared over r plus g. And so the radius in this case is the length of the pendulum. We have that. We have g, it's 9.8. Once I take the square root of root 2gh, it's just going to be 2gh. And I have the mass. And h, by the way, is going to be r as well. You might recognize that when I plug all those numbers in, I get about just shy of 1 Newton. When I plug them in, I get 0.93 newtons. So that is the answer for part C, which is the tension, 0.93 newtons, the tension in the string. One modification that could be made to double the period of oscillation to the pendulum. This question requires you to recognize that period is affected only by length. I get 2 pi, this is a constant, times the square root of L over G. So the only thing that's changing, the only thing I can change is the length. I would have to go to a different planet in order to do that. If I solve this for L by dividing both sides by 2 pi, this becomes period over 2 pi, and that's going to be equal to the square root of L over G. And then I could take the square, I could square both sides in order to get rid of that square root sign. And then the left-hand side becomes period squared divided by 4 pi squared. When I multiply 2 pi, I get 4, or when I square 2 pi, I get 4 pi squared. And then I get L over G on the right-hand side, and I could just multiply both sides by G. So I get G times T squared over 4 pi squared. The only thing that I'm interested in is L. So I can see that period is equal, or I should say proportional to, I'll draw that fish symbol, is proportional to the square root of L. So if I want the left-hand side to go up by a factor of 2, if I want that to go up by a factor of 2, then I should recognize that I need to increase the right-hand side, the value of L, by a factor of 4. Because if I were to put a 4 in for L, the square root of that is 2, it would increase by a factor of 2. So I would need to then increase the length by a factor of 4. I would write that out, and that would be my answer in part D.